All right, everybody, let's talk about the giant planets, okay? Giant planets, super cool, really cool. Um, we want to explore the outer planets, which are the giant planets, describe them, and talk about the atmospheres of the giant planets. So, beyond Mars and the asteroid belt, you reach the realm of the giant planets. The temperatures are lower, water and volatiles like methane condense as ice instead of stay as gases. The planets are larger, further apart, and accompanied by huge numbers of rings and moons. Compared to the giant planets, the rocky worlds near the sun, like us on our little mud ball, seem insignificant. They're very small. The four giant planets are Jupiter, Saturn, Uranus, and Neptune, and that's what this chapter is about. So let's explore. We want to describe an overview of the composition of the giant planets, chronicle the robotic exploration of the outer solar system, and then summarize the missions sent to the gas giants. Jupiter's mass exceeds all the other planets combined. That's crazy. Jupiter and the other planets, in order to accomplish this huge amount of mass, what are they made out of? They're made out of gases, ices, and rocks. Those are the three main types of things. The gases are hydrogen and helium. When we say ices, we don't mean like ice cubes. It's an astronomer term. Ices just refer to anything made of oxygen, carbon, and nitrogen. It doesn't have anything to do with ice in terms of like frozen water. Oxygen, carbon, and nitrogen can combine and become water, methane, and ammonia, those things. So when we talk about ices, that's what we're talking about, water, methane, and ammonia. Jupiter and Saturn are dominated by gases. That's why we call them gas giants, so hydrogen and helium. And Uranus and Neptune have more methane and ammonia, so they are called the ice giants. So that's the difference. So again, they're not made of ice cubes, but oxygen and methane and things like that. So there are some major challenges with exploring the outer planets. It takes decades for a spacecraft to reach the outer planets. That's a problem. Instead of the months it takes to go to the inner solar system. And it also takes hours for the signal to reach these spacecraft. So let's say on the way to Saturn, a space probe encounters a problem and says, NASA, what do I do? Because robots can do that sometimes if we tell them what to do. It might take us several hours to get the signal. And then we go, oh crap, we have to send a signal back there. By the time it gets there, it could be too late, okay? So that's an extra challenge when it comes to dealing with things in the solar system. These are the abundances of the material, so it's about 75% hydrogen, about 24% helium, and then these smaller amounts of the other ices, okay? And you can see by type, gases, ices, and then the rock, like iron. Okay, these are the spacecraft that have flown to the outer planets. You can study that for some fun. You can see it's been pretty steady since the 1970s till today. The main ones are Juno and Cassini that are the most advanced around Jupiter, and the one Cassini just crashed into Saturn. So you can see here how Earth, really close to the sun out there. These we had Voyager 1 and 2 do the tour of the solar system along with Pioneer 10 and 11 that stopped by, like look at Voyager 2's path. It launched, hit Mars, hit Saturn, went to Uranus, went out to Neptune. It's got some really nice pictures in the 1970s. So the giant planets, we want to describe the physical characteristics of them. General appearance, rotation of the giant planets. We want to describe the composition and structure of the planets, compare and contrast the internal heat sources, and describe the discovery and characteristics of the giant planets' magnetic fields. So this is the basic properties of Jupiter, their distances, how long it takes to orbit the sun. You can see that goes like Kepler's third law. In terms of the mass, so 300 Earth masses in Jupiter, that's insane. They all rotate very quickly, look at that. Jupiter only takes 10 hours. They all take about 10 hours to rotate. So that's how long a day is on Jupiter. It's rotating very quickly, if you imagine that. Okay, this is Uranus. Uranus has a weird tilt. Okay, so Uranus you'd expect the rings to be that way. But Uranus and its ring system are this way because it's tilted almost 98 degrees. Okay, so that means it's rotating this way as it goes around the sun. So it's rotating on its side. It was toppled over. It was hit with something, we think, a long time ago to make it do that. So if you look at, you got your ices and your rocks at the core. okay, of the outer planets. So you can imagine if all this gas wasn't surrounding Jupiter, it would be a rocky planet like Earth or Mars or any of the other ones. But the fact that it has all this gas is what makes it so huge. So that's pretty cool. So basically Jupiter was just held on to a lot of the gas that the sun formed out of the same material. Saturn too, and this is why a lot of solar systems have 2 stars in it. If Jupiter was 10, 12, 80 times bigger, it would be a star. It would be an actual star. So almost Jupiter. Internal heat sources. All planets generate their own heat, mostly from the friction from gravity and just smashing everything around. It generates 4 million billion 100-watt bulbs of energy every day, which is the equivalent amount of energy absorbed by the sun. So it's generating as much heat as it's absorbing, which is insane. This makes Jupiter's atmosphere a cross between a planetary atmosphere like Earth, where it's heated by the sun, but also a stellar atmosphere where it's heated from the inside out. So that's kind of interesting physics thing. Saturn generates about half the energy of Jupiter. Uranus and Neptune are different. Neptune has a small internal engine. Uranus emits no measurable heat. Very cold. The magnetic fields of the planets. You can see here how the Uranus is tipped over almost completely on its side. Everything else is north-south, north-south, north-south. There's Uranus. North-south is sideways. Okay, they have strong magnetic fields because their planets are rotating. It's stronger than those of the terrestrial planets. The shapes of the magnetic field are similar to that of a bar magnet. Jupiter is like in there, and this is its magnetic field in radio waves. So it's a very, very, very intense place to be in terms of radiation. Jupiter's magnetosphere, we've talked about Earth's magnetosphere. Jupiter's magnetosphere, after it interacts with the solar wind and gets blown across the solar system, it actually reaches the orbit of Saturn, which is crazy. So when you have spacecraft orbiting Saturn, and as Saturn passes into Jupiter's magnetic wake, or vice versa, whichever one gets there, then you can actually see it on our spacecraft. So that's just shows you the example. And this is a problem for spacecraft because that means Jupiter's radiation is very strong near it. So spacecraft can't survive near Jupiter for a really long time. So that's why Juno orbits a highly eccentric orbit. So get in, take some measurements, get out. Get in, take some measurements, get out. Stay most of the time away from the planet. Okay, so the magnetospheres of the giant planets are huge, much bigger than Earth. They interact with the solar wind. They create radiation belts, just like on Earth, and the aurora. They also emit radio waves, which we can study with antenna here on Earth. Okay, the atmospheres of the giant planets. We want to discuss the atmospheric composition of the giant planets, describe the cloud formation and atmospheric structure of the giant planets, and then characterize the giant planets' wind and weather patterns. We want to understand the scale and longevity of storms on the giant planets. So these are the atmospheres of the giant planets. Again, I'm not going to quiz you on any of this, so you don't have to memorize any of this. The point is just that we've studied this, we kind of know about it, and you can see just the differences in the depths and altitudes of the atmospheres. So when we talk about the altitude is the kilometers, basically from what we consider the surface, but there isn't an actual surface. This is really cool. This is the hexagon at the bottom of Saturn, and you can see how it's broken up into this almost Satanistic worshipping pentagram thing. 1, 2, maybe that's not what that is. I'm a bad Satan worshiper. Okay, I don't know all the tricks. All right, but you can see this circling around. Okay, don't worship Satan. That's not cool. So the winds. This is really important because Jupiter, the cloud bands of Jupiter, right? By the way, there's James Van Allen. He's the one who figured out the radiation belts. And that's at the University of Iowa. Okay, so the winds of the giant planets. So if you look at Jupiter here, you can see that okay, what is this line showing you? This line up and down, this is, if the red line is on the right side, the wind blows this way. If the line is on the left side, the wind blows that way. And so you end up with, on Jupiter, I'm going to exaggerate it here, if this is the line, the wind goes toot, 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 and that's what causes the cloud bands to show up on Jupiter. So the cloud bands on Jupiter, those winds, those change in winds, just create that shape. And you can see on Saturn, at the center, almost all of the wind is blowing in one direction, which is my favorite band. And then you have Uranus and Neptune, which don't have much differentiation in the wind. That's it, though. We don't, that's just your general overview. The main thing that you want to take away from this chapter is that the outer planets are basically made out of the same things as stars, and that they could be rocky planets like Earth and Mars if they weren't covered in all this gas. And that comes back to the idea that there was this giant cloud of gas, and then it collapsed down into the sun. So there's your sun in the middle, and then all the little planets, and then out here some of that gas ended up around a giant, becoming a giant planet instead of being a star at the center. It just didn't quite hold on to enough, so Jupiter is not a massive star. It is it's a big planet. It could have been a small star, but it just didn't have enough stuff. So that's it. See ya.